So hi, everyone. Thanks for having me. I'm very happy to be back here in Darmstadt, where I did my PhD a couple of years ago with Thomas. Now in a different role. Now I'm working for Zama, and we do mostly FHE, but recently also a bit of MPC and zero knowledge. And I'd like to give you an overview of what we do and how we do this. And I'll use the blockchain or a blockchain scenario and use cases from that world to show you how you can apply the protocols that we'll look at in this workshop in practice. This is joint work with a lot of people from Zama. Their names are on the slide here. I'm not going to read them, but we have a great team there. So I just want to mention that this is not my work, but the work of everyone at Zama. So to motivate, why am I talking about blockchain besides it being a huge casino and everyone just gambling money there? There are some actual applications that you want to use this for, where this is actually useful, and it's here, and it's probably gonna stay with us for a bit longer. So we might as well try to make use of it and try to make the best of it. And our motivation really is to bring privacy into the game. So how can we have these amazing use cases, and how can we make them more private with the technologies that we have with FHE, with MPC, zero knowledge? To give you some examples, in the blockchain world, you have classical ERC transfers, so sending money from A to B, making sure that no one can spend more than they have, that everyone gets what they're supposed to be paid. And at the same time, we try to do this as private as possible. So we want to keep balances private, we want to keep the transaction amounts private, and still we want to have these security guarantees that everyone is getting paid properly. There's decentralized ID, where you want to identify yourself, you want to store your identity information on the blockchain, so it's immutable to some extent. Some more advanced applications like blind auctions. You want to do this such that the bids that you're making in an auction remain private, so that no one can outbid you just by knowing what you did bid for a certain item. This happened, for example, with Constitution DAO, where they were trying to bid on a physical copy of the US Constitution. And it was a public auction, so everyone know what the DAO was bidding, so they could just outbid it and stole, well, not stole, but they won the auction instead of the DAO that tried to get this copy. So with a blind auction, you could do this in a more privacy-preserving manner by keeping the bids private, or even keeping the winner private. There's also on-chain gaming, so you can imagine a card game where no one can tamper with the randomness and no one can actually see what the cards are that are on deck. This is just a random assortment of use cases for why the things that we're doing do actually matter in practice, and what kind of cool things you can do with it. And now we want to look into the properties that we have in a blockchain. We're going into security 101, if you will, the confidentiality, integrity, availability properties of schemes. And in the blockchain world, things look like this. You have a lot of integrity because blocks are hashed, and they have to have a certain structure, and they only get into the blockchain if they are actually valid blocks. You also have very high availability because it's a decentralized system, and everyone agrees on the blocks that get in, and it's replicated all over the world. But the confidentiality is very low. Yes, you do have pseudonyms, so there's no names really attached to the addresses that float around. But you see all the transactions; they are all public. All the balances are public. You can track money from A to B, and so the confidentiality in a classical blockchain as they exist today is relatively low. There are solutions that use zero knowledge to ameliorate this, to improve this. But in many cases in the blockchain world, zero knowledge is just used as a performance measure. You sort of aggregate transactions, and you make use of the succinctness properties of zero knowledge proofs in order to actually speed things up instead of making it private. There are exceptions to this, but I want to focus on FHE and MPC and how we can do this differently. So the goal that we want to achieve, ideally, so that's like the ideal world, would be to have all these properties fulfilled to the fullest extent. And we want to look into how we can do this, or if we can achieve this with MPC and FHE. So I've said the three letters already. What is fully homomorphic encryption on a very, very high level? It's a semantics or an encryption scheme. It can be secret key or public key. I'm showing the public key version here. And to just give you an idea, what you can do with it is that you can operate on encrypted data. You can operate on ciphertext, so operate on data that you're not seeing, but you can still do meaningful things with it. Same as in an MPC protocol. And in fact, you will see on the next slide, it is actually very similar to this. So here you have parties on the left that encrypt their their data with a public key, send the ciphertext into the FHE algorithm, if you wish. There you do operations on these ciphertexts. You compare them, you add them up, you do whatever function you want to evaluate on them. And then some person with a secret key can decrypt the result and gets the output of the computation. And now MPC on a conceptual level looks very similar, except there are no keys really. You do some sort of secret sharing, or you do garbled circuits with oblivious transfer, exchanging these wire labels. But you can actually do the same thing. You can have parties that are involved in the MPC computation put their inputs into the MPC computation and run the algorithm interactively and get an output and send the output to some party or to all the parties that are supposed to learn it. So you can also, in some sense, operate on unencrypted data or secret shared data. And the properties that we want to have from both of these algorithms is that it's private. So you don't want to leak more about your input than what you can learn from the function output that is, of the function that is applied to the inputs. You want to have correctness, so the thing should compute what it's supposed to compute. And you want to have robustness, ideally, at least in the real world, you want to have robustness, so you can tolerate a certain amount of cheating parties that try to make the computation fail or try to tell you that something is happening that is actually happening. So as we've seen, these two protocols, they are different, but they're also very similar at the same time. They're so similar that you can, in fact, build an MPC protocol from FHE. And Gentry did this in his thesis, I think, in 2008, if I'm not wrong, where he proposed an MPC protocol built from FHE as a primitive. And people who have been at Real World Crypto might recognize this slide because I blatantly stole it from Nigel Smart, who made the first version of this talk. And I also took the Rockstar theme that he used to denote the parties in this protocol here, namely Alice, Bob, Charles, and Dave. These are all Rockstars, for those who don't know. And they want to run this MPC protocol. And if you have a cloud that does FHE computation for you, you can do the following protocol. At first, you run a threshold key generation protocol. That's as in every encryption scheme, you need to generate, it's a public key encryption scheme, you need to generate the public and the secret key. Everyone gets the public key, and in this version of threshold key generation, all of the parties, they get a share of the secret key. So no one really knows the secret key as a total on their own. They only have like a part of it, and they need to come together in order to make use of it. And then for computing on their private data, what they do is they simply encrypt their private messages, MA, MB, MC, and D, with the public key. So it's a plain FHE encryption. And they send their ciphertext into the cloud for storage and for data processing. And then the cloud does the FHE computation. It applies this function f on the encrypted inputs and gets a result that is the function f applied to what's inside the ciphertext. And this is gets sent back to the parties, and then they come together and run a so-called threshold decryption, where they interactively figure out a way to decrypt the ciphertext by applying their shares in a joint manner. And then they learn the output f, which is the function f applied to the plaintext inputs. Yeah. So in some sense, you see, it uses FHE to do the evaluation, but threshold decryption in itself is inherently an MPC protocol. So these two domains are really very closely related to each other. The protocol that we've just seen is very cool in the sense that it has low round complexity. You're just sending the inputs, getting the outputs back. And the communication complexity is independent of the function that you're applying, because the function is really just applied on the cloud, on this compute side. It doesn't depend on the size of the inputs or the size of the outputs. However, in the way that we've seen it here, it's only passively secure, and obviously there are many attack vectors. So what I try to focus on in this talk is how can we make this a bit more secure, or how can we make it secure without inferring too much overhead so that we can still use it in practice, and how can we actually map this into a blockchain scenario. So for this, we introduce a few new parties. We have a blockchain, which is right there in the middle. We also have a few helper nodes, the threshold nodes, the Beatles. They're here to help because with a little help from my friends, we can do things much more easily. And on the right-hand side, we have the validators. These are a band called Always. They're written with 2 Bs, so they were the perfect candidate for the validators. Also to bring a bit more diversity into the picture. so we don't just have old white dudes on the slide here. And we still have the users. They have the inputs. They want to put their data in. Threshold nodes are here to help with the computation for setting up the keys and the decryption. And the validators, they're doing the computation. And we'll see how this goes in the next slide. So at the start, we have the threshold key generation, where the beetles come up with the public key. They put it on the blockchain for everyone to see. It's public. Everyone can access it, can just read it from there. And they also, as before, have shares of the secret key. So they need to come together to do operation that requires the secret key to do a decryption or a re-encryption. That's important. The inputs get in the same as they did before in the protocol with the cloud. It's just a regular encryption under the public key, sent into the blockchain, so everyone gets access to these ciphertexts. And then the computation doesn't happen in a single cloud. It happens on all the validators. And this is not actually a bad thing, because the computation is relatively cheap. We're talking milliseconds or maybe seconds if it's a very complex thing that you're computing. But this is perfectly fine to replicate over a bunch of nodes that do computations anyway. So we can just do it several times in parallel. So they do the function evaluation in FHE, send back the ciphertext blockchain. From there, the threshold nodes can pick this up, run the threshold decryption, and then either post the plaintext output to the blockchain or send it securely to some party who's supposed to learn it. So this is just a simplification here. The output doesn't necessarily need to go to the blockchain here. It's just one way of making it public in this example. And that's the protocol. Now, what can go wrong? Because obviously in the real world, a lot of parties might do bad things. We have Angus here. He's the devil. He's the bad guy. If you go back to the cloud scenario from before, obviously the cloud can just compute something that is not what it's not supposed to compute. Like instead of applying the function f, it applies a function g, and no one will figure out because it's doing this on encrypted data. It sends back a ciphertext. How will they know that they didn't apply the right function? In the worst case, it could just be the identity function that gives you the straight back one of the inputs from one of the parties. And if you decrypt, you get the input from Alice in this case. This is something we want to avoid. And in the blockchain scenario, it's pretty easy to avoid as long as we have an honest majority of validators, because we can just do a majority vote and we'll figure out that 4 parties send us a ciphertext F and 1 party send us a ciphertext G. So obviously this ciphertext G is either something gone wrong in the transmission or the party is actually actively cheating. So Angus has corrupted the guy here. And he tried to fool us into believing that G is actually the output, while it's not, because the other 4, they do agree that CTF is the output. So we have solved this problem just by assuming an honest majority on the validators. And this is a perfectly fine assumption because these validators can be the same nodes that run the blockchain, and there we already assume an honest majority. So this is perfectly fine. In MPC protocols, we have a property that's called independence of inputs. So in a sense, that means that you cannot choose your input based on the input of another party that has submitted it into the protocol before you. This is important both on the theoretical side for security proofs, because you need to be able to extract inputs from the dishonest parties for the simulator to make the proof, the simulation-based proof go through. But it's also important on the practical side. And we want to avoid this in our systems. And a classic technique that gets used to achieve this property is just a zero-knowledge proof. So you're proving that you're knowing the thing that you're secretly transferring into the protocol. And this basically tells you or gives you the property that no other party can take your input and claim that it's their own, because they cannot prove that they know the plaintext that corresponds to it. So this would be the attack that you see here. In this case, Angus Young has corrupted Bob Dylan, and he just steals the ciphertext of Alice. But you would say, wait a minute, if I get the same ciphertext twice, then I know that someone has copied it. But with FHE, you can actually re-randomize a ciphertext. So you wouldn't notice that this is a copy, because you could just add an encryption of 0 or multiply it with an encryption of 1, and you could still have the same semantically, the same message embedded in a different ciphertext. So you wouldn't know that someone basically just stole your ciphertext. So in order to prevent this, I already spoiled it in the slide before, we're using zero-knowledge proofs to ensure that the value that you're sending into the blockchain, that you actually know that you know the plaintext message that corresponds to the ciphertext that you're sending into the blockchain. And at the same time, we also need to prove something else, because we're dealing with an LWE scheme here. The encryption scheme that we're using at Zama is called TFHE, for Torres FHE. and it's based on the LWE assumption. And why is proof of plain text knowledge not enough? And the reason is shown on this slide. If you look at a homomorphic encryption scheme like Al-Gamal, you have the property that every ciphertext that you see is an encryption, a valid encryption of some message in the message space. But in LWE, not every ciphertext that you see is an encryption of a valid message. It might be just random garbage stuff. And the reason is that the noise that you have in the ciphertext, this small e here, it needs to be small enough to not drown out the message that is actually hidden in there. And that's actually precisely the LWE assumption, that you need to distinguish random noise from an actual proper encoding of the message in the ciphertext. So we need to not only prove that we have knowledge about the message, we also need to prove that the message is actually small enough to have a meaningful ciphertext in this case. And we have two schemes for that. But to give you more idea why this is a problem in practice, if the E would be too big, that would lead to two essential problems. A, it could break robustness. And B, it could even be a denial of service attack, because decryption would fail. And then what do the parties do? They have no idea why it failed. They need to start the protocol again. But what's even worse is if E is chosen just slightly too big, this gives you a selective failure attack. And this is a very powerful attack because this could actually lead to a leakage of private data. So then if the protocol fails or not depends either on the secret key or on the input of other parties. And just by observing these failures, you could learn or infer information about their other parties' private inputs. And this is obviously a very bad thing. So I guess that's the motivation for why do we need to prove that this E is bounded by a certain length. And we have two measures for this. One is an MPC in the head-based proof by a bunch of French people. Their names I forgot, but they're on the slide in the end. They have a fast prover. It's actually post-quantum secure. The proofs are relatively large. And they're using an MPC in the head assumption to build these proofs. And I find this very funny because we're using an MPC assumption to build a zero-knowledge proof to secure an FHE scheme that builds an MPC protocol. So it's like all the way around all the techniques that we have to build something very cool that actually works in practice. And the second option that we have is by Benoit Libert. It's based on vector commitments. The prover is a bit slower. It's only classically secure, but the proofs are very small. So this is a good thing if you want to post them to the blockchain, actually. What else can go wrong in this protocol? Well, if we have Angus down here, he has corrupted George Harrison of the Beatles, and now the threshold parties do something stupid. Well, an adversary could leak information about the secret key to an outside party or to some other party. It could try to corrupt the decryption operation to make you believe that the result of the decryption is actually something that it's not. Or it could simply just not do anything and try to run a denial of service attack, so you'll never learn the output of the computation. So what can we do about this? Well, the threshold protocols that we're running, they have a robustness property, and we can actually tolerate a certain amount of corruptions. Theoretically, this could go all the way up to T less than n.5. So with 4 parties, you still only have 1. But if you had 5 parties as threshold nodes, you could actually tolerate 2 corrupted parties, and you would still be able to run the decryption and the key generation. In practice, and what we have implemented, we're dealing with T less than n/3. So we can tolerate 1 out of 4 or 3 out of 10 or whatever, 13 out of 40 corruptions, and we are still able to run the protocol securely, robustly, and privately, and it's all going very well. This is a summary of a work that we published at the WARC workshop at CCS last year, just to give you an idea of what we needed to do to make this actually work in practice. We needed to implement secret sharing over rings, which sounds easy on paper, but it's actually not if you actually implement this stuff. The reason is that TFHE works over a modulus Q, which is 2 to the 64. So you cannot do this in fields. You need to do it in rings. And this requires a bit of maths in the background to make this fly. We have an operation for noise flooding. I don't want to go into all the details here, but we need to expand the ciphertext to a larger domain so we can do the noise flooding. which actually drowns out information about the inputs. And we weren't sure if this would be practical, but the performance numbers that you see on the slides here actually show that it is, and that you can do this even with 40 parties on an internet-like network in less than 1 second for a ciphertext, and you can run this in parallel. So this would also work just fine if you do this in a bigger system. And we have security proofs done by Nigel, simulation-based, which is nice, and to a good security level that you want in practice. So now, to sum up and to come back to the CIA properties that we seen at the beginning, how does this look if we apply this? If we use the system in practice, how does confidentiality, integrity, availability look? If we assume that we have less than n over 3 corruptions, well, we get a lot of confidentiality, a lot more than we have in a plain blockchain system. Integrity is still there because we haven't changed anything there. The availability goes down a little bit, unfortunately, because if you think about this threshold assumption, then T+1 parties can decrypt and they can break the availability by just not doing anything. We cannot recover from more than T+1 adversaries if they try to disrupt the system working. So in some sense, we're trading in a little bit of availability. It's still very high. It's still pretty good in a practical system, but it gives us a lot of confidentiality as a trader. So in that sense, this is what we achieve with the current solutions. And to give you one more outlook in what other systems can do, the alternative would be a full threshold system. They would achieve perfect confidentiality, but then a single party could bring the whole system to a halt if they try to attack it. So this is not a trade-off that you want to do in practice in a real-world deployment. There are still some open problems that we're also working at and that I encourage you to look at, namely the threshold assumption. How can we improve it? Maybe by using proof of stake or other measures, by making the parties stake the money on the blockchain so they actually have a financial incentive to stick to the protocol. Or is publicly verifiable MPC an approach that we can take to make the parties behave honestly? Is it too heavy in practice? We don't know. How can we make sure that the parties don't just sell their shares of the secret key? An idea would be to have them run the computation in a trusted hardware environment like Intel SGX or a hardware security module, such that they never really get access to the share itself, just an interface to interact with it. And also, what can we do in terms of key recovery? Can we, like if a party just never shows up with their secret key share, is there a mechanism that allows us to regenerate the shares? Obviously, there's a resharing procedure that I haven't shown you before, but is there something better that we can do to tolerate these kind of attacks? These are the references. I think there's a recording and the slides are online, so you can look them up later. And with that, I'd like to conclude. And I thank you for your attention, and I'm happy to take a few questions.